In this video, we will be talking about models and properties of multiplication for whole numbers. Have you heard people ever just say, why can't kids just learn to memorize? Can't they just learn math facts by flashcards or skills and drills? All we need is just worksheets. These kids aren't learning their facts because they're just lazy. Well, why do we need more than flashcards and worksheets? Why? Well, if students can memorize facts, then they can forget them. But if students will just understand these facts conceptually, then they can determine these multiplication division facts, even if they can't automatically recall them. Some kids are really good at memorizing and some aren't. So this is a common core for grade 3. Notice they have a lot of product and factor in here talking about it. So, the product is the answer when you multiply two things together, and the factors are the two numbers that we multiply together. So, we're going to talk about some models for multiplication in this video. So, we've got 5 different types of models. So we're going to start with a repeated addition, okay? So whenever you do repeated addition, or basically any of these models, you need to think of the multiplication facts, such as 5 times 4, is the first number represents the number of sets that you have, and then the second number represents the number of objects in the set, okay? Or when it comes to repeated addition, you need to think of this as 5 sets of 4, okay? So first, let's talk about what multiplication is. It says for every whole number, a and n, then n times a means I'm going to have n sets of a's. So I've got a n times. Again, if you think of it as 5 times 4, we're going to have 5 sets, 1, 2, 3, 4, 5 of 4s. And then we add them together. Okay, so if n is 0, that's the fact that you have 0 sets. So if you have 0 sets, then the answer is going to be 0. Okay, so we're going to multiply 5 times 4 a bunch of different ways. Okay, so the first one is what I just talked about, repeated addition. So 5 times 4, I want you to think of that as 5. You've got 5 4s, 5 sets of 4. So that will give me 20 to begin with, okay? Here's a visual way of representing it. It's known as the set model, or some people call it equal groups. Notice I have 5 sets, and how many are in each set? We've got 4 in each set. So 5 sets of 4. On a number line, you would say 5 times 4 by going out 4 and then starting at that end. So you would start here at 4 to do the next arrow, and you would go 4 more, and that will give you 8. 4 more, that will give you 12. 4 more gives you 16 until you get all the way to 20. Okay, so that's 1, 2, 3, 4, 5 times that you were going out 4 units. Okay, so 5 sets of 4. And you're going to, so the final answer isn't going to be those where we stopped, it's going to be 20. Now our area model, 5 times 4, that stands for 5 rows of 4. So your rows, here's all your rows. I've got 1, 2, 3, 4, 5 rows. And there's my columns. 5 rows, and there's 4 columns. 5 rows and 4 columns. So anytime you are showing it with an array, and that's what this is called, an array. So an array really is just a set of items that you put in rows and columns. Okay, it can be numbers, it can be ducks, whatever you want it to be. But you want to have 5 rows, and there's 4 in each row. Okay. Here's some concrete ways of showing it with base 10 blocks. Notice that I've got 5, 1, 2, 3, 4, 5 rows again, and I've got 4 columns. So you can show it with base 10 blocks, or you can use those little cubes, okay? Or you can use the little units, the units in the base 10 to make that. You could use counters, or you could use your Unifix cubes to do the same thing, where you have 5 rows, and in each row has 4 items, 4 Unifix cubes, 4 counters. It's 5 times 4. With my Reckon Rec, notice how many rows of Reckon Recs I have. 1, 2, 3, 4, 5. So I have 5 rows, and in each row, I've got 4 beads. Okay, so 5 times 4. So you can watch this video to learn how to use Reckon Recs to multiply in your own classroom. Now the key is we are only going to be in the classroom. I only have 2 Reckon Recs for each group, right? So like this one right here, we have 2 Reckon Recs for each group. So that means I can only go this far. Okay, in our class, that's all we have the manipulatives for, right? So this is, one of you would have this one of you would have this one. So we couldn't do 5 times 4. So if I give you 5 times 4 to use a Reckon Rec with, you may have to switch it. You may have to switch it to 4 times 5 because we have 4, you can make 4 rows. Okay, and that's just because we don't have enough Reckon Recs. Okay, so then you would have 4. There's one set from one partner, and there's the other set from the other partner, and then you'll have 1, 2, 3, 4, 5 on each one of these. So in class, you may be asked to multiply 5 times 4 using a Reckon Rec. You can't. You would have to switch it to show it using a Reckon Rec. Okay? Anyway, but here's a video to reiterate what I was just saying about how to multiply with Reckon Recs. Okay? So here are some other ways to multiply. Okay? One is called skip counting. Okay? So with skip counting, it's exactly what you might think. If it's 5 times 4, I'm going to multiply by 5s. 5, 10, 15, 20 to get up to 20. And I did it 4 times. Okay. 3 times 5, 3, 6, 9, 12, 15. So 4 times 7, you would do 4, 8. You would count by 4s. 4, 8, and you do it 7 times. 4, 8, 12, 16, 20, 21, 27. So that gives me 7. And it's okay for you to use your fingers, right? It is okay for you, like in this case, you may know how to count 5, 10, 15, 20, 25, 30, 35, 40. You might be used to counting by 5s, okay? So you would use your hands to count on your hands each time. So 5, 10, 15, and my fingers, I'm using my fingers. So 5, I put up one finger, 10, the second finger, 15, the third finger, 20, the fourth finger, and I know I'm done. Okay. And 2 times 6, do the exact same thing. 2, 4, 6, 8, and I just keep on going all the way up to 12. And I'm using my fingers as I count. So I would hold up one finger here, 2 fingers, 3, 4, 5, 6. Once I get to the 6th finger, I know that I'm done, and that is 12. So I would say 2, let's say 2, 4, 6, 8, 10, 12. Okay, so skip counting is one way that you can multiply. Another way is called the Cartesian product. Okay, and so this helps students to understand, because you will have students say, when am I ever going to use multiplication? I know how to add. I'll just add a bunch of times. Okay, so you could give them this as an example. We're going to learn to make a tree diagram, and you'll be making some tree diagrams in class. So, how many outfits can Bubba make if they have the following in his closet? All he has in his closet is 5 pairs of pants. That's all. And all he has in his closet is 4 shirts. And you may say, why? Surely people have more than 4 shirts in their closet. Well, it makes your tree diagram smaller, but it depends on the kid. My kid went to college. My son went to college. He had 10 shirts. That is it in the closet. Anyway, okay, so let's say he has a brown shirt. So with his brown shirt, he can make how many outfits? Excuse me, I meant brown pants. With his brown pants, he's got 4 shirts, so he could make 4 outfits. Brown pants with a yellow shirt, then the next day a pink shirt, the next day the purple, and the next day the orange shirt. So he could go 4 days in brown pants, and he would have 4 outfits. Okay, but he's got blue shorts. So he could have 4 outfits with his blue shorts as well. He could then have 4 outfits with his black shorts, right? Or black pants. I keep saying shorts. He could also have 4 outfits with his white pair of pants. And finally, 4 outfits with his green pair of pants. So the total would be 4 plus 4 plus 4 plus 4 plus 4. That's 1, 2, 3, 4, 5 fours. So he has 20 outfits. So that is a tree diagram to show how we could multiply 5 times 4. 5 pairs of pants and 4 shirts. So that's called a tree diagram, or it's also called a Cartesian product. All right, so flashcards are great, but with every flashcard, you only get one multiplication fact. So if I had a flashcard that said 3 times 4 equals 12, that is all I would get out of that one flashcard. The kid would look and say 3 times 4, okay, 12. Let's flip it over. Yeah, that's correct. Okay. Whereas you can make fact families. So you can have these triangular shaped cards that are fact families. And with these fact families, it tells you a ton of information, not just 3 times 4. Now it has that down here, 3 times 4. So that's one thing that they have. Okay. But you could also go backwards and say 4 times 3. So that is another fact out of this fact family. Now, we're not supposed to know how to divide yet, but that also shows me that 12 divided by 3 equals 4, and 12 divided by 4 equals 3. So instead of one flashcard for one fact, you've got one triangular flashcard, and it has 4 facts. It shows the relationship of 3, 4, and 12. Okay, so what would be the fact? What would this fact family card look like for 5 times 6 equals 30? Well, your 30 is going to go up in the top of your triangle, and the 5 and 6 are going to go at the bottom. And then you'll put a times, because 5 times 6 is 30, and then put division in between the 30 and the 5 and the 30 and the 6, because 30 divided by 5 is 6, 30 divided by 6 is 5. So this is a great alternative to flashcards. I will try and remember to bring in some wrap-ups. I'll show you that. You can also Google it. Wrap-ups is a great thing. I used to keep wrap-ups in my car. So whenever my little kids would be waiting in the car line for me to pick up my big kids, I'd just throw them a wrap up and they had to do, 2 or 3 wrap ups in the car while they were waiting on their sibling. Um, so these fact families are also called number bonds. Do you see that these guys, this one and this one, is very similar? I just sort of turned that on its side. So my number bonds show me that 3 times 4 is 12. And then these guys are a division, okay? But it essentially breaks that 12 into 2 factors, 3 and 4. So 5 times 6 equals 30. That number bond, you're going to put 30 in the big circle and then the two factors in the small circles. So that's also called a number bond. It's very similar to your fact families. So I want us to show 2 times 5 in all these different ways, the ones that we've talked about. Okay, so skip counting. I'm going to have 2 sets. I'm going to have 2 sets of 5. So 5, 10. Okay. Repeated addition, the same thing. I'm going to have 2 5s. So 5 plus 5 is going to give me 10. So that's how I do repeated addition. Equal groups, I'm going to have 2 groups of 5. So there's my 2 groups, and I've got 5. And it doesn't matter what you put in those. I just put X's, but you can put smiley faces or counters or however you want to do that with your students. So your array, remember your array, this is going to be your rows. So you're going to have 2 rows with 5 in each row. And then here's my fact family. 10 is 2 times 5, right? And there's our division. Okay, I'll do this again. So my skip counting, I'm going to have 4 sets of 2. So that's going to be 2, 4, 6, 8. So my answer, would be 8. Repeated addition, again, I'm going to have 4 2s. So 2 plus 2 plus 2 plus 2. Equal groups, I'm going to have 4 sets of 2. So there's my 4 sets, and I put 2 X's in each one. My arrays, I'm going to start off with my rows first. So when I drew this, and when you draw it with your class, you could say, okay, I'm going to have my 4 rows, and each row has 2 in it. So I draw that first column, draw this column first to set up how many rows I have. Okay. And finally, my fact families. So 4 times 2 we said is 8. So 8's going to be at the top and the 2 and the 4 is going to be at the bottom. All right. Let's do one more. Skip counting. Where folks mess up, and I might have messed up top, but I'm going to have 5. I'm going to have 5 3s. 5 sets of 3. So that will be 3, 6, 9, 12, 15. So there's, whoops, didn't mean to do that. There is 1, 2, 3, 4, 5. So that's how I do it with skip counting. Repeated addition, same way. I'm going to have 5 3s. So I write 3 down 5 times, put a plus in between them. For my equal groups, how many sets am I going to have? I'm going to have 5 sets, and each set is going to have 3 in it. For my arrays, I'm going to have 5 columns. Sorry about that. I'm going to have 5 rows. So I draw this first, 1, 2, 3, 4, 5, and then I go back in and fill in. I'm going to have 3 in each of those. Makes it a little bit easier when you're trying to draw those arrays. And lastly is my fact families, or it could be called number bonds. So they may ask you to draw, I may ask you to draw a number bond, which would look like this. You would have your 15, and then you would have your 3, and your 5, and there's your number bond. Okay, so now we're going to talk about properties of multiplication. So we need to find out if our whole numbers are closed under multiplication. So again, that means I've got got bunches of zeros, bunches of ones, bunches of twos, all the way up to forever. Okay, is it closed under multiplication? If I grab, one of these and one of these, and I multiply them together, will I still get a number that is in my box? Okay, so that answer is yes. So here's an example. I got a 5, I got a 4, multiply them together, I'm going to get 20, and that is in my box. Okay, so whole numbers are closed under multiplication. Remember, they were closed under addition. They were not closed under subtraction, but they are closed under multiplication. Okay, is multiplication commutative? Can I change the order? So in this case, here'd be an example. Is 3 times 5 the same as 5 times 3? Okay, well, here is a visual model. Here is my rectangle. It has it's got 3 rows and 5 columns. Okay, or 5 times 3, I've got 5 rows with 3 in each. And notice that all I did was take this guy and turn it and just flip it up on its side. So I've got the same number of blocks. So 3 times 5 is equal to 5 times 3. So the associative property says if I keep the same order and group them differently, but keep the same order, will I get the same answer? So again, here is a visual, okay? So we're going to start off with this guy, 5 times 4. So notice this bottom one. There's 5 here and 4 here. So 5 times 4. And then I have 3 of them. 1, 2, 3. So 5 times 4 is what, 20? And then times 3. So if I made a block out of that, I would have 60 little blocks. Okay, I could take that, and so I could split it differently. I could say 5 this way times 3, and I would have 4 of those. So instead of grouping these guys together, I've now grouped the first 2 together, right? So if I put all these guys together, I just squish them down, okay? And I put all these guys together and squish them together, I'm going to get the same block. 3 on this side, 3 on this side, 3 on this side. 5 on the bottom, 5 on the bottom, 5 on the bottom. 4 this way, 4 that way, 4 that way. Okay, so that shows that the associative property works for multiplication. Okay, what about identity? Multiplicative identity. What would I have to multiply 5 by to get the same thing back? 1. That should be 1. I don't know why I put 0. So I should be multiplying by 1. So that 1, instead of, I wish they called it the identity of multiplication. But instead they call it like multiplication. They replace the shun with iv. So multiplicative identity is 1. Okay. Multiplication of property. Property of 0. Anytime you multiply by 0, what are you going to get? 0. Because that's saying I have 0 sets of whatever, right? The distributive property, whenever I teach distributive property, I talk about giving out cookies. Okay, so I'm going to take these 5 cookies, and I'm going to give them to that person, that kid. Okay, then I'm going to take the 5 cookies and I'm going to give it to the next person. So the distributive property, I'm giving those cookies to those kids in there. Okay, so 5 times 3 plus 5 times 4. That's my distributive property. Okay, again, here is my visual aid. Okay, so this big piece, this whole big thing, is your 5 times 3 plus 4, because 3 plus 4 is 7, and let's count 1, 2, 3, 4, 5, 6, 7. So I'm distributing this 5 to all 7. Okay, or I could, instead of doing that, I could split it right down the middle right here, or I guess it's as close to the middle as I can, and I break it apart. So now I'm multiplying 5 times 3 and 5 times 4. So if I put these guys together, you're going to get this guy right there. Okay, so it's visually shows the distributive property. I just thought that was pretty cool. So we're going to use the distributive property when we do mental math. Whenever you're thinking 13 times 7, I don't think 13, because if I do, then that's 3 times 7, which is 21, and I've got to regroup and trade, and I just can't do all that in my head. So instead, I split it, and I think of this as 10 plus 3, right? And then I distribute my 7 to both of those. So I'm going to distribute my 7 to my, I'm going to distribute my 7 to my 10 right there, and distribute my 7 to my 3. So I wind up with 70. That's this guy right here, 70, and 21. And I add those two together and get 91. Let's do it again. 24 times 6. So I'm going to split it into 20 and 4. So 6 times 20, not the 4, 6 times my 20 is going to give me, 100, and well, I'll use what I've already done. So my 6 times my 20 is going to give me 120, and my 4 times my 6 is going to give me my 24. When I add them together, 144. So that's how your math teachers are able to multiply in their head. Okay, they're not thinking carry the 2 or carry the 1, or as we are supposed to say now, regroup and trade. That's not how they do it. They think of it essentially left to right and use the distributive property. So does the distributive property work with subtraction? That's right. That's right here. Does it work with subtraction? Well, let's look and see. So I'm going to get, yes, it does. I'm going to have 5 times 4 is 20, and 5 times 2 is 10. If I subtract it, I get 10. Or I could say 5 times 2 here, and I get 10. So either way, whether I work it without distributing or work it with distributing, I get the same thing. Okay, so now we're going to get a little fancy. Okay, so you may remember this in your Algebra 1 class as the FOIL method, where you take the X and you distribute it here, and then you take the Y and you distribute it there. We call it FOIL. I call it cookies and lemonade, because I distributed my blue cookie and then I distributed my lemonade, my red. But for visual learners, this is a phenomenal trick. Okay, so we can go ahead and do the distributive property. That's what Freddie FOIL is. That's what I call it. So this is the FOIL method, and this is the algebra method. Okay, but your kids may not have had algebra, right? So so they can use, this is also used in Algebra 1 classes, it's called algebra tiles. If you're taking Math 212, the next math for elementary, you'll probably learn about algebra tiles. But notice this is X plus Y right here. So I'm going to put the X here and the Y there. So the length of this would be x plus y. And then on the top, I'm going to put a z and a w, so that would be z plus w. And then I just fill in these. I multiply these together. X times z, that gives me my xz. X times w, that gives me my xw. Y times z gives me my yz. Y times w gives me my yw, and that's exactly what we got here. Here is it's called an area model that would represent that problem. So notice it's the area. It's a big old box, right? If I was figuring out the area, I could figure out each of those four and add them together. Okay, so that's called an area model. This is, let's see what grade this is, if it has it down there. Yes, grade. This is grade 4. So it's just straight out of a 4th grade textbook. Do you see it's got the area model, right? And it's got the distributive property. So it shows exactly what we've been talking about. Also, notice it then shows the partial products, adding the partial products, which we've talked about in the past. So anyway, so that's 4th grade. Is there another way you could use the distributive property to solve that problem above? So I want you to notice that all of these textbooks are very different than what you probably had growing up. When I was coming through, they didn't say, show me another way. They said, this is the way you do it. They didn't show any kind of visual anything. Okay. It was always just memorize this. But now they show multiple ways, and then they say, hey, you come up with your own and let's see if it works. Okay. You're trying to get your students to not just memorize, but to think mathematically, think logically. Okay. All right. You could also do that distributive property backwards. Okay. So that's where if you notice, you have a 5 here and a 5 here. So I'm just going to take the 5 out, and then I've got these guys left over, 3 and 4, and so that stays in the middle. Do you remember what that's called? Everybody's favorite math word, factoring. Okay, so you're going to have some little mini factoring in this section. So once again, I'm going to take my 5 out. I'll take that 5 out and that 5 out, and then I will have these guys left over, the A and the 3. So I take my 5 out, and then I have my A and my 3 left over. Okay, over here it's a little bit weirder because it's all letters. Okay, but notice I've got here I have 2 X's and here I have 1 X. So I know I've got 1 X in common. So I take that 1 X out, and then I wind up having it's on the outside, and I still have another X left over. Okay, but this 1, why are we putting a 1 there? There's not a 1 sitting here. There is technically an understood 1 sitting there. Okay. But also, I always think, okay, let's distribute back. Okay. So I always tell my students to double check. So if I was distributing back, that would give me x squared. But if I did not have the 1 there, if that was gone, that's all I would have. I wouldn't have my plus, right? So I need to have that plus 1 there. So when I distribute, I get the same thing I started with. All right, that's how you know if you did your factoring correctly. Okay, this last one. All right, so what do those guys have in common? Well, they have an M in common, so I'll put an M out there. And then they have an N in common. So I'm going to put 1M because I only have 1 in common, and 1N because I have only 1N in common. So I put those on the outside. And then I go back through and I figure out what's missing. So on the outside of this one, I have an M and an N. So there's my M. But oops, I need another N, right? So that's why I put that in there. So this one's done, check, okay? But this one, I've got M and N, so I've got one M, one N, but I've got an extra M, so that's why I put that one there. So you may remember that from Algebra 1. Okay, last properties are our properties of exponents. So first thing we need to talk about is what in the world is an exponent. Exponent, of course, is this little bitty number up there, okay? All that means is that's how many times you're going to have this number, that number 2. That number 2 is called the base. It's on the bottom. So I think about that song. It's all about that base, about that base. So it's the bottom, right? It's the bottom number. It's also, I was cheerleading sponsor when I taught in high school. So they were the base. The base is on the girls on the bottom of the pyramid. Okay. So the base is the bottom, and then the exponent is the high flyer. So you're going to have 3 of those 2 sitting there. So a to the n means I'm going to have a n times, however many times, however big this number is, that's how many of these a's you're going to put out here. Okay, so that's an the definition, I guess, of an exponent. So now we have the product rule. The product is you've got a to the second times a to the third. Well, a to the second times a to the third, that means I'm going to have 2, there's my 2 a's there. And then there's my other 3 A's there. So how many total do I have? I've got what? I've got 5 of them. Okay. So you have a 2 and a 3 and you got a 5. So what did you do to the 2 and the 3 to get a 5? You just added them, right? Okay, so we're just going to add those numbers together. Of course, math people have to be geeks and put all letters up there, but you're just going to add those together. Now, the next one, I call it the peep and Tom rule. No one else calls it the peep and Tom rule. It's called the power of a something. There's the power of a power, the power of a product, and the power of a quotient. Okay, it is all the same rule. Okay, it's all the same rule. So I just call it the peep and Tom rule. So the peep and Tom, first you might need to know what a peep and Tom is. I call this the peep and Tom. Some people call it an exponent. Other people call it a power, and it is a power and it is an exponent. That's the problem. It's because when you say, okay, look at the exponent. Well, are you talking about the 2 or are you talking about the 3? So I just made up a word. I said it's a peep and Tom. It's the one that's, see, there's the window right there. It's the one that's peeking in the window. Okay. So I call that 3 the peep and Tom. So whenever you have a peep and Tom, that means I'm going to have 3 of these guys right there, right? I'm going to have 3 of them. So there they are. There's 1, 2, 3. So now let's count them. 2, 4, 6. So I'm going to have 6, 8 to the 6th. All right. So I have a 2 and a 3. I got a 6. What did I do to a 2 and a 3 to get a 6? We're going to multiply them together, right? So m times n. So anytime you have a peep and Tom, a number right here outside of your window, you're going to multiply. So this is called the power of a power. Okay. This one, the way I explain it in my Algebra 1 class is they are looking into just a single bed. Okay. Now here we got a double bed. You see, you got 2 people in it. It's a double bed, but it is the exact same thing. Okay. You are multiplying these exponents. 2 times 3 gives me 6, and 3 times 3 gives me my 9. Okay. But other math people don't call it the peep and Tom with a double bed. They call it the power of a product because those 2 are multiplied together. So it's called the power of a product. There's also the power of a quotient. Our book doesn't talk about it, but you can probably figure it out. It's when it looks like this. You won't have any of these. But it's the same rule, right? It's the same exact rule. So power. So you can have single beds, you can have double beds, you can have king size beds, you can have tons in here. Okay, but it's the same rule. Okay, the Peep and Tom rule. All right, the quotient rule. That's when you are the quotient. You're dividing. So x to the fifth divided by x to the third. So you're going to have 5 of them on top, right? 5 x's on top and 3 on the bottom. And now we're just going to cancel out the ones that we can, right? So we're canceling those out. What do we have left? We've got x to the second. All right, so you have a 5 and a 3, and I got a 2. What are we going to do to those exponents? The 5 and the 3. Yeah, we're gonna subtract them. Okay. So anytime you have you're dividing, you just wind up subtracting those exponents. All right. Now here is the zero rule. Okay, so I'm going to develop the zero rule. X to the third over x to the third. So you've got 3 x's on top and 3 x's on the bottom. Now I put a 1 there. Now, I have a lot of students say everything canceled, so it's 0. But let me show you. If I made it 2 over 2, you know you've got 2 pizzas divided by 2 people. Everybody gets 1 slice, 1 pizza, right? Okay. So when everything cancels, you have 1 left. Okay. Now, let's use this rule that we just talked about, the quotient rule. Okay, so instead of having a 5 here, I'm going to have a 3 there. Okay, so I'm going to subtract 3x to the 3 minus 3. I'm subtracting these guys, right? So I get x to the 0. So I started off with the same thing. So I got 1 was x to the 0 and 1 was 1. Well, those are equal to each other. If you remember in section 3.1, we did some and I said anything to the 0 power is 1. And I said, I'll explain why later. Well, here is your explanation. Okay, that's why anything to the 0 is 1. So here are some, we're going to use some of these properties of exponents to answer these questions. Okay, so we went over the properties, now let's use them. Okay, I'm going to go ahead and start with a big old trap. Okay, now what makes this a trap is the 8's. Let me change that 8 to x squared times x to the third. Instead of having an 8 here, we're going to have an x there, right? So what is this guy? We don't have a Peep and Tom, so we're not multiplying. So we're going to add those together, and I get x to the fifth. Do you notice that I did not change my base? My base didn't change. People have no problem with that when the base is a letter. When it's a number, I get a whole lot of, instead of 8 to the fifth, I get a whole lot of 64 to the fifth. Okay, so this number right there, notice it did not change. That is my Mongo trap. Lots of people miss that on the test. Okay, you're going to keep the base the same. All right, here's another type problem. I'm going to split that 12 and I'm going to factor it. 12 can be split into 3 times 4. It can be split into 2 times 6 also. But notice I've got a 3 here and I've got a 4 there. So I'm going to split this 12 into 3 times 4. Okay, so I split it. Notice that this was raised to the 4th. So I'm going to split it in 3 to the 4th times 4 to the 4th. All right. And so now I have something that looks like that, right? I've got 3 to the 5th times 3 to the 4th. I'm going to add those exponents. So that'll give me 3 to the 9th. Notice I didn't multiply the 3's. It's 3 to the 9th. And then I'm going to multiply those. So I'm going to get 5 plus 4, my exponents. That's going to be 4 to the 9th. So my final answer would be 3 to the 9th times 4 to the 9th. Okay, so we are simplifying it. So we are taking this, sorry, didn't mean to do that. We're going to take this and separate it so that all I have is 3 to some power and 4 to some power. Okay, you'll have several of those in your classwork. All right, now we'll go back the exact same trap that we had before. We're going to have it again. Okay, so if that was x to the 5th over x to the 2nd, we know from our rule up here, our quotient rule, what do we do to these numbers? We subtract them, right? So I'm going to do the same thing. I'm going to subtract those two numbers, my 5 and my 2, and I'm going to get x to the 3rd. Notice that this guy never changed. Okay, so this guy is never going to change. We're going to subtract my 5 and my 2 and get 3. So that's 7 to the 3rd. I get lots of students that will cancel it out and give me 1 to the 3rd. And then Maven simplified a 1. That is not the case. Okay, it's 7 to the 3rd. And then again, anything to the 0 power is going to be 1.